Friday, if you all come forward, a small group. Maybe we'll give 2 minutes. Let's see if others are going to join. Okay, let's get started. So, where did we leave yesterday? Relations? So, we saw 3 fundamental equations from Lacey, which are velocity is a function of F and R, and then area is also a function of velocity. Then we have velocity So these are the 3 fundamental relations that Lacey gave based on the empirical data. Now based on this, we also derived some relations. So the weighted perimeter P as a function of discharge Q. We got a new relation for the velocity. So we have derived these relations yesterday. Right? Are we leaving something? one more. SF and small q, discharge per unit. So now we are going to use these equations to design a channel. Now if I want to design a channel, what data do I require? Discharge. So how much water I want to draw. So let's say we are given a discharge Q, and then we would know the sediment size in that site. So if you go to the site, collect some soil samples, and if you do the sieve analysis, you would get the D50. So if you get the D50, then F is 1.76 square root D. Yes, so D50 is the mean particle size. So let's say we have Q and F. Now, based on these two informations, we need to design a channel. And let's say we want to design a trapezoidal section. And with some known side slopes. For example, I would take the side slope as half horizontal to 1 vertical. Now I want to know what is this bottom width B and what would be the flow depth Y. And all I know is only the discharge and the sediment size. So where do we start? So we have equations, let's number them, 1, 2, 3, 4, 5. So we have 5 equations. So which one do we pick first? Velocity. So given Q and F, first what we can do is calculate velocity. Now, once we calculate velocity, then what is the unknown actually? So we have two unknowns, B and Y. So once we get the velocity, we have the discharge. So what can we get out of velocity and discharge? Area. So now we have got the area. So this is the area that we need to maintain for the channel. Let's say we get some x meter square. So we know the discharge, we have the velocity, and we get as x meter square. And we also have two unknowns, B and Y. So you can also calculate the area based on the trapezoidal section with the two unknowns, B and Y. So this is our equation. So this is one of the equations that we arrived at. Now based on discharge, what else can we calculate? Perimeter, P. And this is units meter. So this is also again a function of B and Y. So this becomes our second equation. So we have two unknowns and two equations. So if you solve for equation 1 and 2, then you would get B and Y. And what else is unknown? So we got the section, cross section, but we need to fix the slope, the longitudinal slope of the channel. So you can use any of these equations. Yes, because we are using the same fundamental relations. So the difference between Lacey's and Kennedy's is, here we are calculating the slope required, whereas in Kennedy we would use the natural land slope and use that in our calculations, whereas here we calculate what is the slope required, and then we make sure that the land has the same slope as this is. Otherwise we need to do some cutting and filling in the land to make sure the slope is maintained. So that is the difference. So this, we calculate the slope, whereas in Kennedy we use the natural land slope. And what is the other difference between Lacey and Kennedy that we discussed yesterday? So about something about the bed and the slope. So what are these on the bed? Turbulence eddies. So these are turbulent eddies. So the other difference between Casey and Kennedy is, in Kennedy he only considers turbulence or eddies coming from the bed, whereas in Lacey's he considers from both sides. Now, why is this eddies important in both the theories? So they are considering eddies as some main phenomenon, and why is it? So what is the objective that we are trying to achieve by designing through Lacey and Kennedy? So there are two conditions that we want to satisfy. So one is no erosion, and whatever sediment has entered into the channel, it has to remain in suspension. So now put into context of the sediments and this turbulence. So we are talking about suspension and then some turbulence that is mixing the flow. So if there is mixing in the flow, then the sediments would be in suspension, so they would not get a chance to get deposited. So that is why in both the theories we are considering eddies as the main phenomena for keeping the sediments in suspension. Whereas in Lacey he considers eddies from the side slopes as well. In Kennedy he only considers turbulence from the bottom. Now let's do an example of Lacey. Let's say we want to draw 50 meter cube per second, and F, the silt factor is 1.1. Now we need to fix the section for this channel. So what is the velocity? 0.86. And what is the area? Q by B? 57.5. And what is the equation in terms of B and Y? What trapezoid? By plus y square upon 2. Okay. And what is the perimeter P? Give me the value first. 33.5. And then the equation is y root 5. Now you have to solve these two equations to get B and Y. So what is the value of B or Y? 29.35. 29.35.
Y is 1.9.
1.9. 1.89. So when you solve these two equations, this is what you should get. And what about the slope? So tell me one on slope. You can use any equation. Or you can simply use this, which has F and Q. So 1/549. So approximately 1/5400. So these are our channel dimensions, and this is what our bed slope should be when we design the channel. So now the question is, how do we look at bigger picture? So we are designing a canal based on a discharge Q, so which is at a particular location. But when you want to design a canal, we have a river, and the canal takes off from the river. Let's say we only have one canal that's going from the river, and let's say this is, I call this as 0 kilometer. So 0 kilometers from the entry, and this would be 1 kilometer from the entry. 2, 3, 5. Now let's say between 4 and 5, I have 5,000 hectares of land that I want to irrigate. And between 3 to 4, again I have 5,000. Here I have 5,000, 5,000 each. Now some discharge is entering here, Q1. Let's say I want to say this Q. And between each sections, I want to denote as Q1, Q2, Q3, Q4, and Q5. Now, what would be the relationship between Q and Q1? So, which is higher or lower, or are they equal? So, it would be equal. What about Q1 and Q2? Which is higher? Q1 is higher. So, as you see, the discharge is decreasing. So, your channel section should also be changing because your discharge is changing. So, when we talk about longitudinal sections, you need to design multiple cross sections along the length of the canal. And you usually start from the end. So let's say here I have a discharge Q5, and we consider that, let's say there are 10% of losses because of conveyance from 4 to 5 kilometers. Now here, if you want to design this section, you would consider Q5 plus the losses. So 90% efficiency. So the discharge that you would be using to design is Q5 by 0.9. So here, you would be considering the losses that happen between 3 to 4, and the same discharge should pass through 4 and 5. Right, so you need to consider the losses between 4 to 5 as well. So if discharge Q is entering, then when you design a channel, you need to consider the losses in all the sections. So if there is 10% loss in every section, then you cumulatively add that loss to discharge Q. So that's why you calculate what is the discharge here, and then calculate what is the loss. Let's say it's 2 meter cube per second is the loss. When you come to Q4, you add that Q to 2 meter cube per second as a loss here. So now you're designing this section for Q4 plus the losses that can happen here. So progressively you start from the end of the canal and move to the top and design each section. And each section can have different slope. Again, so if you are using Lacey's theory, then it gives you a slope, so you need to maintain that slope as well. And some places, so let's say I'm taking in water from this side and I'm looking at the canal slope. Let's say this is the natural bed slope. So at the entry, it is at higher elevation and it is decreasing as we go. But there is a sudden change in the elevation at some location. So here you need to design section, and what we do is generally provide a fall. So instead of allowing it to follow the natural slope, you provide a fall, and then you let the channel to follow the natural slope again. So if this fall is higher, let's say if this is 10 meters or more, then we can have some small hydropower plant, some small turbine you can use there. So whatever the water has is, because it has a 10 meter elevation difference, you can divert the water through the powerhouse, and then you can generate some little power and then let the water flow again. So this is how the longitudinal section might look like if you have changes in the elevation. So to bring in the context of Unit 1, so in Unit 1 we discussed about different types of crops and the water requirements for crops, right? And when we want to design a channel or a canal, this Q, or let's say I have 5,000 hectares here at the bottom, and the discharge is Q5. So this discharge Q5 comes from the water requirements for the crops. So whatever we have learned in duty delta in the first unit, we will be using those concepts to calculate what discharge is required at this section. So in your exam, the problem might be giving you only the crop data, what is the duty delta, and you need to calculate what is the discharge, and for this discharge you have to design the canal section. So you may not be directly given the discharge Q. So you need to bring in the concepts from Unit 1 and design the discharge first, and then for this discharge design the canal section. Right. So this is about the longitudinal section. Now we will look at the cross section again. So far we have been looking at the trapezoidal cross section. So we are only focusing on the channel where the water is flowing. But when you construct a canal, you also need to provide some embankments or banks so that the water, when there is a flood situation, the water cannot overflow it, right? So what we do is generally provide some berm. So this position is called berm, where from the top of the canal you provide a horizontal portion and then you provide banks on top of it. So this is our canal through which the water is flowing. And these are the banks. Now in some locations, because we are actually designing a trapezoidal section, we have to cut the land some places and we have to fill in some places. And whatever we cut from the canal section, you can use for filling in the banks as well, right? So we have the two processes that we need to do, cutting and filling. Now, what would be the most economical scenario in cutting and filling? Yes, so whatever we cut, if we are using that for filling, then that would be the most economical scenario. And this can happen, let's say the canal depth is D1 or D, then there would be only one depth for which this can happen, where cutting and filling are equal. So whatever the amount that you are cutting from this section, if it is entirely being used for the banks, then there could be only one possible depth, D1, where cutting and filling can be equal. So this depth D1 is called balancing depth. So now let's do an example to calculate what would be the balancing depth for a scenario. So let's say I have a bottom width of 18 meters and the side slopes for the canal are 1 on 1 and the side slopes for the banks are 2 on 1. And the top width of the bank is 2 meters and the height of the bank from the horizontal level is 3 meters. Now for this, we need to calculate what is the balancing depth in this scenario. So how do we do it? Yeah, so yes, so let's say we are looking at per unit length of the canal. So then you do the area, so calculate the area of trapezoid and then equate it to the area of the two banks together. So you would get the balancing depth D1. So this is 3 meters. So what is the equation for D1? Area of cutting in terms of D1?
18D plus D square.
18D plus D square. And what about area for filling?
48.
48 square. So if you equate the area for cutting and area for filling and solve for D1, you would get. So just going back to the longitudinal section. So designing the section between 4 to 5 kilometers. So if the discharge required based on the crop requirements is, let's say, Q4. Now for this Q4 there is 10% loss or there is 90% efficiency. So we are considering Q4 by 0.9, and we also should consider the losses that happen between 4 to 5. So then that would be 0.1 times Q5. So when we design the section between 3 to 4, this is the total discharge that we need to consider. And when you consider the discharge at this section, how many hectares of land would you consider? So let's say at this section, how many hectares of land would you consider? So I want to design this section and the discharge. So whatever the discharge is flowing through this section, it has to satisfy this 5,000 and it also should satisfy this 5,000. So for calculating the discharge requirements, you should consider cumulatively whatever is below this section. So everybody got D1 2.35? That's fine. Okay. So this is end of unit 2. So we have finished unit 2, but we are delayed by 3 classes. I missed 2 classes. We'll try to cover up in unit 3. Or I'm thinking during the mid-semester period, I will record 1 or 2 lectures so that you can watch after your exams, which would be very simple topics, like what is defining waterlogging. So all of us know what is waterlogging and problems. So those theoretical aspects I will try to cover in the recorded videos that you can watch later, and we'll try to catch up. Yeah. So that's it. Thank you.